Okay, so the first question and second question and so forth are all about multiplying probabilities. So basically, one thing you need to realize is that here the offspring is not born yet. So you don't know A, if it's male or female, that's why it's a diamond, and B, you don't know anything about the genotype yet. Unlike the people that are born, you already know some things about the genotype because you know the phenotype. So what we're asking is, what's the probability that this offspring here ends up having the disorder? And so it's autosomal recessive. And so in order for that to happen, it would need to be autosomal recessive, homozygous for that. So that in the end is what the probability of this offspring being little a, little a. So in order to do the probability of that, you have to go back each generation and figure out the probabilities there. Now, usually it's going to be a thing where maybe you have one generation you don't know, or one of the two you don't know, and so you'd have to multiply two things you'll see in a second. But in this case, there's lots of generations you don't know. So you're going to have to go back all the way to the first generation and multiply probabilities. So in the end, because it's a rare disorder, it's passing through this family here. That's why these individuals, they're big A, because they married in. It's unlikely they have disorder. So what you're asking in the end is you want two little a's to come together. So what's the probability that the little a went through each generation? What's the probability it got passed on here and then got passed on here again and then gets passed to the kid? And what's the probability it gets passed on here and then passed on here again and then passed to the kid? So you need all those probabilities. And because you have a lot of generations with this, it's a big A, but then you have a blank. I'm trying to do these in different colors. Because you have a big A, but then you have an unknown. And that just means, remember that it could be big A, or big A, little a. It's unclear from the information you have. You have to figure out what's the probability of each of those being big A, little a. So the idea here is, in order to pass it down to generation number 4, it has to exist as a carrier in generation 3, a carrier in generation 2, and then we know it's carriers in generation number 1 because they made an affected offspring. There we go. We know that this individual is little a because it's affected, and so that means these parents must be carriers. That's known already. But then after that, we have to figure out the probability of each of those offspring leading to this baby are carriers. So we need K and I, or you could say 3, 1, 2, 3, 4. We need generation 3, parent 4, and then 5. 3, 4, 5. In order to get this baby, we need both of these parents to be carriers. We know that they're not little a because they're not colored in. We already figured that out. So we need them both to be carriers in order to get this baby. But, so we need to figure out the probability that they're carriers. So let's look at their parents. In this case, both of those parents, we know one of them, but not the other one. So in order to make a carrier offspring here, then we need this parent to be a carrier, right? Because this parent has no little a to give. We need it to be inherited through this parent. But we don't know that parent. So let's go here. So we need generation 2, 1, 2, 3, 4, 5, 6, 7, to be a big A, little a. And we need generation 2, 1, 2, 3, 4, 5, right? That has to be a carrier as well to pass it down to be big A, little a. So what's the probability of that? And then we have to go back one more generation, right? So looking at these parents, now we need to know the probability of these two parents giving these offspring. So if we start at the top, generation number 1, what do we know? Big A, little a, crossed with big A, little a. Now we want to know what's the probability of getting a big A, little a baby, right? That's what we're looking for here. So if you do that cross out, you can see that that probability is, oh, I'll do this for you. So just so you can see why. Okay, so you have both parents produce both types of eggs and sperm. So they can come together in all the different combinations. Now, the deal is here, though, that you know that this offspring, this one, and this one for that matter, but let's just look at this. You know that offspring only has these two options because it's not colored in. It does not have the disorder. So that means you know for sure it's not little a, little a. That's what the hint was talking about, knocking a box out. So of the options left, what's the probability it's big A, little a? Well, it's this one and that one, so that's a probability of 2/3. So what's the probability of this individual being big A, little a? 2/3. In fact, the same parents, so what's the probability of this individual being big A, little a? 2/3. So let's write those in here. So 2/7, that's 2/3 probability of it being big A, little a, and same for this is 5. Yeah, 5. It happens to be the same because it's the same parents in this case. All right. So erase this so we don't multiply again. So then we go, well, if those two parents are big A, little a, actually, let's look at the parents here. So now we have generation number 2, right? And we want to know generation number 3. We want to see what's the probability you get carriers. So generation number 2, let's cross these two parents to see what this offspring might be. So we know it's this crossed with this. So what's the probability you get big A, little a? Well, you could do the Punnett square if you need to. You only have one option of eggs. So in this case, it's not, this is what you know it to be, but we've already figured out from here that it could be big A, little a, and so that's what you're crossing. From that parent, you have 2 options of sperm, potentially. So how many of these are the big A, little a? Well, 1 out of 2. So what's the probability that you get a big A, little a baby from this? 1/2. So that is the probability that this individual, so that's 1, 2, 3, 4, 5, that's our 3, 5, 1/2 that they get a big A, little a. And then you can do the same thing here for this parent, and you can actually see that it happens to be the same cross. So the probability for 1, 2, 3, 4 being big A, little a is 1/2. So now we have the probability of this individual, the probability of this individual, that's these two, the probability of this individual and that individual, that's these. Great. And now let's say if all that's true, what's the probability of generation, should be this color. That's all generation 3. What's the probability of this generation 3 producing a little a generation 4? And if you do that, you can tell it's 1/4. So that's the probability for this last cross here. And then you have to just multiply them all together because it's every probability multiplied. So in the end, what do we have? We have for this first generation here, let's do the orange. We have 2/3 for this parent, 2/3 probability for that parent. Then we go to the next generation, 2/3 or 1/2 probability for the third generation for both those parents. And then the last generation here, what's the probability of generation number 4? So if you multiply all that together, 2 times 2 is 4. The bottom multiplies to 144. If you simplify that, it's 1 out of 36. So it's a 1/36th chance that you get that, I guess it's horses, but this offspring would have the disorder, because it's a probability that each of these is a certain way. Like I said, I wouldn't make you do that many, but it's not unreasonable that I would have you do like one round. And then this idea is important here, that if you know a phenotype, sometimes you can get rid of boxes, or boxes meaning possible genotypes, and that changes the probability. So you do the same thing for the autosomal, the sex-linked or X-linked recessive, but now you're going to use, the nice thing about this is you always know the male, right? Because the male has to be this or this. There's no other option. It's the females when they're like that you're asking what's the probability that usually that she's a carrier. What's the probability she's a carrier? And so you have to look at the parents to figure that out. And then I think that there's probability of 2 things happening, like both diseases, so you do the probability of each of those multiplied and so forth.